Hello dear students, welcome to Learning Chemistry is Easy and Fun, a channel dedicated to making chemistry a little easy for the student, for a learner, and once it becomes easy, it's definitely fun. And the best part of the fun is that you can share it with everybody. There's no loss, no gain, nothing. It's pure joy. Let us start with the lesson for today, quantum numbers. This is lesson 17 on the series of videos on structure of atom. What is quantum number? It's simply an address for the electron. Like you could write down your address. Let's suppose from your address you want to go to a place called as Chemistry Learner, door number 365, Unblock Fun, Street YouTube, City Google. So from your address, you have to go to Google, right? So how far is that from your place, right? So that is the first thing that we need to estimate. That's what is given by the principal quantum number. Principal quantum number is denoted by the symbol n. The value of this is 1, 2, 3, 4 and so on. If you recall, we had also given it the values K, L, M, N and so on according to the Bohr's concept. What does this tell you? It tells you the distance of the electron from the nucleus. So you are the nucleus in this structure and these are the places where you have to go to. So the value of N gives me an approximate idea of the distance of the electron from the nucleus. So if I have the principal quantum number as 1, the electron is closer to the nucleus compared to the principal quantum number 2, which in turn is closer to the nucleus than principal quantum number 3. So what is it talking about? If you see, I'm simply drawing the Bohr structure of the atom. So it corresponds to the orbit in the Bohr's concept. Only thing is, Bohr said that the electron is exactly at this distance. The quantum mechanical model says it is approximately within that distance. A little in, a little out. It's approximately to be found there. So n is equals to 1 means first, n is equals to 2 means the second orbit and so on and so forth. As the value of n increases, so does the distance from the nucleus. So the value of n gives us an idea about the average distance of the electron from the nucleus. This is also validated by the mathematical expression for radius 0.529 into n square upon the atomic number, in the West value being in angstrom units. If you are unclear about this expression or you want to know more about this, there is a specific video on this channel where you can access the details of this mathematical treatment. What else does this principal quantum number tell us? It gives us an idea about the energy of the electron. So E1 is less than E2, is less than E3 and so on and so forth. So as the distance of the electron from the nucleus increases, so does the energy. This is again proved by the mathematical expression En is minus 13.6 upon n square electron volt per atom. Here, although n is in the denominator, if you notice, the energy has a negative value. And we've already discussed this in the previous videos. Fourth point. What does n tell us? The maximum number of electrons in an orbit, given by 2n square. Now this is a very simplified version. We shall be proving this correct as we advance in our learning and go on to the fourth quantum number. So n is equals to 1, number of electrons maximum number of electrons. Please understand here, it's the maximum number of electrons. It can be less than that, but it cannot be more than that. So the maximum number of electrons in the first orbit is 2, where n is the value of the principal quantum number. Second orbit 8. Can you do the calculations for me and give me the value for n is equals to 3? Just pause the video and give me the value. Yes, it's quite oral. 2 into 3 into 3 gives us a total of 18 electrons. The maximum number of electrons in the third energy level is 18. How is this principal quantum number relevant? This principal quantum number is nothing but the Bohr's orbit. Simply, it's given a more technical term because it goes well with the Schrödinger wave equation. It explains the two spectrum that we have observed for hydrogen, the absorption and the emission spectrum. Again, we have already discussed these in the success of the Bohr's theory. Just to give you an idea again, if the electron jumps from lower energy level to higher energy level, it absorbs energy and we get absorption spectrum. If on the other hand it comes back from a higher energy level to a lower energy level, any of these, from 4 to 3rd, 4 to 2nd, 4 to 1st, it emits energy because it doesn't need that extra energy. So it emits out energy and we get what we call as the emission spectrum, as was explained by Bohr. The next quantum number we shall be doing is the azimuthal quantum number, denoted by L. Now let us come to azimuthal quantum number, also called as the orbital angular momentum quantum number or the subsidiary quantum number. Now where is this going to lead us? It's going to lead us to the street. The address we said was, the city was Google and the street is, yes, YouTube. So let us see what is the street that we are talking about here. Azimuthal quantum number is denoted by the symbol L. Its value is defined by the value of n. That means if n is 1, what are the possible values of L? The value of L can be from 0 to n minus 1 for that particular shell or energy level. So what we have over here, if n is 1, the possible values of L are 0. Now n minus 1, 1 minus 1 is 0. So 0 to 0, it's only one value. These are whole numbers. So L is also 0. When L is 0, we call it as sublevel S. So how many sublevels are there when n is 1? Yes, it's only 1. Just like saying that you are in a big school, that's your atom. You are in grade 11, that's your orbit. You are in 11B, that's your sublevel. So in grade 11, there's only one sublevel. Coming to value 2, when n is equals to 2, that means I am talking about the second orbit. The value of L can be 0 or 1. How? N minus 1 is 2 minus 1 equals 1. So that doesn't mean that the value of L is only 1. No. The value of L is from 0 to 1 whole numbers. So I have value when n is 2, L is, yes, 0 and 1. So how many sublevels? This is giving me the number of sublevels. So if I am talking about the second orbit, how many sublevels are possible? Yes, 1, 2. So total 2 sublevels. What is the name given to these sublevels? It's called as the S sublevel and the P sublevel. Come to n is equals to 3. So we start from 0 to n minus 1. Now what will be the value of n here? Yes, it's 3 because I'm talking about the third orbit. 3 minus 1 is 2. So whole numbers between 0 to 2. 0, 1, 2. When L is 0, we call it as, yes, S sublevel. When L is 1, we call it as, correct, P sublevel. Now that's a third one. When L is 2, we call it as the B sublevel. So all in all, in the third energy level, how many sublevels are possible? 1, 2, 3. 3 sublevels. Now for n is equals to 4, what will be the value of L? Although it's written on the board, can you work it out yourself and tell me what are the possible values of L? What will be the sublevels and how many sublevels are there in all in the fourth energy level? Yes, please work it out. Please don't do 0 to n minus 1 over here. That we've already done for finding out the value of L, because this is one mistake I have seen students doing. What they will do is, they've got the value of L over here as 2, so they write 0, 1, like that. No, these are the values which we get from 0 to n minus 1. So this L is 0 to n minus 1 for that particular value of L. So what do we have over here? When L is 0, what sublevel is this? S. When L is 1, what sublevel? P. Correct. When L is 2, sublevel? D. When L is 3, can you make a guess what's the next alphabet I'm going to write? Yes, it's F. We've done the orbital concept in the previous lesson. So it's S, P, D, F. How many sublevels in all? Yes, it's 4. So on and so forth. We can also calculate for the other energy levels. But when we do the electronic configuration, you will realize that we actually don't go beyond SPDF. You'll see the reason for it yourself. What is the relevance of this azimuthal quantum number? First of all, the energy differences are there. The energy of S is less than the energy of P, is less than the energy of D, is less than the energy of F. So what is there is an electron which is there in the S sublevel will have energy lower than an electron in the P sublevel. Does this ring a bell? Does this remind you of something that we've done in the principal quantum number? Yes, the electron can also jump from S sublevel to P sublevel. P to D. Now these energy transitions are small because the energy difference between two sublevels is not as large as between two orbits, right? So what is happening is small energy changes are taking place over here. S, P, D, F. Electron can jump from S to P or come back from P to S and so on. So because of these minor energy transitions which are taking place, we can explain the finer lines in the hydrogen spectrum. If you remember, one of the objections of the Bohr's theory was that the lines that you observe in the spectrum, each line is found to be made up of still finer lines. How do we explain that? So here the major energy transition is made up of finer lines. Just like in chemistry, you don't easily jump from 30% to 90% within one test. How do you do? It's a gradual transition from 30 to 35 to 45 to 65 and finally you are the best. So what we have over here is these are the energy transitions. So that is why this concept goes on to explain the spectrum, the finer spectrum in the case of hydrogen, and also a part of the spectrum in the multi-electron atoms. We shall discuss this later. Now this azimuthal quantum number, as we have seen, gives us the total number of sublevels in energy for any energy level. So first energy level 1, second energy level 2, third energy level 3, fourth energy level 4, and so on. It also gives you the value of the angular momentum. Bohr's concept said that the angular momentum is quantized. If you remember, mvr is nh upon 2 pi. The quantum mechanical concept goes a step further and relates it to the orbital angular momentum, or the subsidiary quantum number, as under root of L into L plus 1 multiplied by h upon 2 pi, where h is our Planck's constant. The quantum number further also helps us to define how many electrons will occupy a particular sublevel. How can we calculate that? By the formula 2 into 2L plus 1. Sublevel S. Now sublevel S means the value of L is. Come on, make a guess. Yes. See, a value of L is 0. So 2 brackets 2 into 0 plus 1. What can you do the calculations? Yes, 2 times 0 is 2, 2 plus 1 is 3, 3 times 2 is 6. Yes? No? Where did I go wrong? Can you tell me? Yes, it's 2 times 0 is 0. So 0 plus 1. 1 plus 0 is 1 into 2 gives me 2. Yes, it keeps the class a little light. So if you have the S sublevel, the number of electrons is 2. So in S sublevel, only 2 electrons can be present. Come to P. When you're talking about the P sublevel, what is the corresponding value of L? 1. Can you calculate the number of electrons over here and give me the value? Go ahead, pause the video, calculate. Calculate also the number of electrons for the D and the F sublevel. I will give you the answer, but first I want you to pause the video, find out the answer. See if you are getting the concept right or not. D sublevel means the value of L will be what? Yes? Yes, it's not 0, 1. D sublevel means the value of L is only 2. F sublevel means the value of L is 3. So how many electrons do you get in the D sublevel and in the F sublevel? Put the value of L as 2, L as 3 in each of these cases and give me the number of electrons which can be present in each P, D and F. One has been done for you. I'm waiting, I'm insisting again and again because I want you to do it. If you do it yourself, the concept will be clearer. Yes, P has a maximum capacity of 6. D has a maximum capacity of 10. F has a maximum capacity of 14 electrons. So you have S has 2, P has 6, D has 10, F has 14. These sublevels are used to define the 3D shape of the area, of the spatial arrangement or the spatial distribution of the electron in an atom. We shall now go on to the third quantum number called as the magnetic quantum number. Please don't lose track and keep a notebook and pencil in your hand for further calculations. Let us now talk about the other two quantum numbers. The magnetic orbital quantum number, the spin quantum number. Magnetic orbital quantum number denoted by ml. What are its values? Its values range from -L to +L, all integers included between the two ranges. Now here if you notice, the value of n had given us the value of L, that is the number of the orbit had helped us to decide the number of the sublevels in any orbit. Now the number of sublevel, as to which sublevel it is, whether it is S, P, D or F, will help us to decide or give us the value of ml, that is the number of orbitals in any sublevel. For example, you are in a particular class, you are in grade 11. Grade 11 has 5 sections or 5 subparts in it. So 11A, B, C, D, E. Now you are in one of the sections of grade 11. What does this tell you? In that grade 11, in what marks range do you lie? You are 30 to 50% holder, 50 to 70% holder, 70 to 90% holder. So that is what this is deciding. Or into how many categories is one sublevel divided is what is being indicated by ml. For example, if we start with the sublevel S, now the range is from -L to +L. So what are the integers between -0 to +0? Yes, it's only 0. So the number, how many values, not what values, how many values of m do you get, gives us the number of orbitals. So there's only one value of m, you get 1. In other words, S sublevel has only one orbital. Now when you will represent this in the form of a diagram, when you do the chemical bonding, you will find that in most of the places this is how it is denoted. So this is S sublevel as well as S orbital, because S is not further divided into any more sections. Coming to P sublevel. Now try recalling your knowledge of the azimuthal quantum number and give me the value of L. Yes, it is 1. The values of ml are from -1 to +1, all integers. So what are the integers between -1 and +1? -1, 0 and 1. In other words, how many orbitals do we have? As I said, see the number of values, not what values. So 1, 2, 3. In other words, your P sublevel has how many orbitals? 3, which you will find is denoted by this indication. So this is your P sublevel divided into 3 orbitals. These is what we had studied as Px, Py and Pz. If you remember in the previous video, we have done the shape of the p orbital. They are aligned along definite axis. Hence this is the quantum number which helps to give the shape or explain the shape of any molecule. Why did we say similar thing about S? Because S is non-directional. Anything round will have no direction. It is symmetric. It is spread equally. So it doesn't have any specific direction. On the other hand, in the case of P, D, F, the orbitals are defined along definite axis. That is why they have directional characteristics and help to define the shape of the molecules. So P sublevel 3 orbitals. Coming to D. What is the value of L for D? Pause the video. Try getting the value of D. Try getting the value of M. Predict how many orbitals are there. When you pause the video, you do it yourself, you will get confident as well. So earnest request, please try this yourself. Try the D and the F sublevels yourself and then match with what answer we are going to do in this video further on. Go ahead, pause and do it. Coming to D, L is 2. So the values of ML here for us would be -2 plus 2, -1 plus 1 and 0. So 1, 2, 3, 4, 5. In other words, my D sublevel, so this is my D sublevel, is divided into how many further smaller parts? Yes, 5. 2, 3, 4 and 5. Now, these names also we had done, if you remember from the previous video, dxy, dyz, dxz, dx2y2 and dz square. All these shapes we have done in lesson number 16. Now we cannot say that dxy corresponds to -2 and dyz corresponds to +2. No, there is no corresponding value. Each of these can assume any value. As we explained earlier as well, that we are just talking about 3 axes perpendicular to each other. So if I am taking this axis as x, this is y, this is z. I can also take this as x, this as y, this as z. So they are just mutually perpendicular to each other. Now try for F. F will be 3. So you'll have ±3, ±2, ±1 and 0. So in all, how many values of F are there? 2, 4, 6 and 7. So your F sublevel is divided into how many orbitals? 7. So 1, 2, 3, 4, 5, 6 and 7. Right? How many sublevels, how many orbitals are there in any, maximum number of orbitals in any shell will be n square. Yes, it is not sublevels, it is the maximum number of orbitals in any shell. We shall verify this in a minute when we do the spin quantum number. As we explained, this particular quantum number helps to explain the shapes of the molecules. It also helps to explain the Zeeman and the Stark effect. Going back to the drawbacks of Bohr's model, where we had said that Bohr's model is unable to explain the Zeeman and the Stark effect. Because according to Bohr, what was there? There are these just main energy levels. You jump from one to the other to the third one, or you come back. There's no intermediate. What the modern concept says is that within one energy level also there are smaller sublevels, and within those sublevels also there are orbitals. Like if you are a 30 to 50% holder student, if you put in hard work and you practice regularly, you will jump from 50 to 70% range, and with further hard work and concentration and being able to understand, you will jump easily from the 70 to the 90 range. But each of these changes will require you to put in energy. So you go from 30 to 50, 50 to 70, 70 to 90 range. But unless you do hard work, this change will not happen. So the same changes happen in the presence of magnetic and electric field. So what happens is, in the presence of the electric or the magnetic field, there are, yes, energy differences within these orbitals as well. The orbitals also split on the basis of the energies that they have. So the electron can now, like you are occupying a particular position in the class. So just like you can move from one bandwidth to another, same way can the electron move from one energy level to another. At present, these are degenerate. The word that we use are degenerate. That means they are all having equal energy. At present, this d orbital has, this d sublevel, all the d orbitals are of equal energy. But in the presence of magnetic and electric field, these orbitals break down. They separate and they will have different energy levels. The details of this you will do when you do go to further higher studies. I don't want to confuse you at this point of time. The same can happen for F and so on. So this orbital, this concept of magnetic orbital quantum number helps to explain and remove a lot of anomalies which were there in the Bohr's concept. The last quantum number, spin quantum number. Now, let me add to this here quantum number 1, 2, 3, principal, azimuthal, magnetic are all a result of the Schrödinger wave equation. This wave concept gave us the idea of finer energy states in any orbit. Spin quantum number, on the other hand, is not so. It has been a result of the observations made by scientists. What does this observation say is that the electron in an atom while it is moving around the nucleus, it also spins on its axis. It can either spin clockwise or it can spin anti-clockwise. So they introduced another quantum number to define it, and it is called as the spin quantum number. It is denoted by S or ms. Its values are very, very simple, plus half and minus half, saying that the spin can be clockwise or anti-clockwise. Again, it is not that plus half corresponds to clockwise and minus half to anti-clockwise. It can be either way. How do we represent it? Now, we're talking about the electron. So now we fill the electrons in the orbital. So the electron, while occupying an orbital, can either have a clockwise or an anti-clockwise spin. An electron can have clockwise or anti-clockwise spin, clockwise or anti-clockwise, clockwise or anti-clockwise, clockwise or anti-clockwise. So what is the maximum capacity of the electrons in the d orbital? Yes, if you see over here, it is 10, 14, 6, 2. This we are going to do in the next video as to how we can have only 2 electrons in any orbital and not more than that. For now, we have done now the address of the electron, how the electron can be detected, or how do we define its position in the atom. Look out for lesson number 18, where we shall be learning how to use these quantum numbers in order to write the electronic configuration. And then you are good to go and teach this topic to anybody. It becomes very, very easy, and so does chemical bonding. If you like the video, please don't forget to subscribe and share, because sharing brings a smile to you as well as me. Thank you so much. Happy studying.